right, this is the 15.4 video. This is on Green's theorem. This is, again, more physics. Most of chapter 15 is physics. So in an effort to keep the videos not ridiculously long, I'm going to just go over the math and leave the physics to your physics teachers. So here, this is page 858. It talks about what we were talking about before with conservative vector fields, the potential function f, the fact that it's path independent. But here it says in this section, so here they're talking about doing, you can't really see it, but work or flux over a closed curve. So this is what's different now. The curves have to be closed. Closed curves will be where they start and stop at the same place. So not open basically, but it's different from the closed and open regions that we were talking about. I don't remember what section that was in, but that was for regions, open and closed regions. This is open and closed curves. So a closed curve starts and stops at the same place. Okay, but here our F's are going to not be conservative. So our capital F's are not conservative here, but that's the two differences. The curves are closed, the vector fields are not conservative. But what we're going to do with Green's theorem is take these line integrals that we've been working with in chapter 15 and change them into double integrals. So it talks here in this paragraph kind of where you would see this, how you would use it, assumptions, whatnot. So it starts with divergence, and this is also known as flux density. So you have your these are going to be two-dimensional. Notice you just have the m and the n. There's no p because there's no k component. So these are two-dimensional vector fields f. And so the divergence of f is the sum of these two partial derivatives. And then here it just gives you a little bit more information about that. So page 860, you can read this on your own, this paragraph above example 1. Again, more information here on page 861. Some stuff here about gases, incompressible. Another idea about Green's theorem, which they introduced this k component of curl. And so we'll get to that on the next page. But here, talking about circulation density. So divergence was flux density. This is going to be now circulation density. So this is page 862. This has to do with like these rotation things. So they have these paddles. They rotate around these paddles. So anyway, you can read more about that here and here. But here's the formula for the k component of the curl. And so we're not going to use these like this. We're going to use them in conjunction with an integral in a minute. So you'll see these same two things appear in integrals in a second, but this is kind of telling you more about what they are. And then here, just again, some more information about it on in the paragraph above example 2. So go back and read that information so you can, it's a little bit more background behind what these things are. And again, a little bit more of explanation of the physics behind it, but we're going to focus on the math because I am a mathematician, not a physicist. So it's probably a good thing. I would make a horrible physicist. Excuse me, I'm sorry, I'm having throat issues today. Okay, so Green's theorem has two forms. There's going to be two forms of Green's theorem. One of them is called the normal form, and one of them is called the tangential form. You don't have to remember that part of it. The part that you do want to remember is this form is for flux. It's the flux divergence. So you have the outward flux and the divergence integral. So notice this is a line integral. This notation indicating that it's a closed curve. And then this, if you remember that, is here. See, that's the same thing. The divergence is this. So what you're integrating is the divergence. So in the previous formula, you had the actual divergence. Here's the integral of the divergence. So notice it's a double integral over region R, integrating. They always have x first in the formula, but you can switch the order up if you want to. Okay, so they have some more information you can read on your own at the bottom. This is 863. So this paragraph at the bottom of the page has some more information. Probably the most important thing in here is the direction, and you need to be going counterclockwise. Counterclockwise is associated with a positive orientation. So if you're going clockwise, that's a negative orientation. All right, in the next formula, this is the tangential form, but the more important part is that it's a circulation curl form. So notice this piece here, that's the same as from this piece here. Right? That was the K component of the curl. Now you're integrating it, so this is circulation, and this is the curl integral. So notice on this one, it was flux and the divergence integral, and here it's circulation and the curl integral. What's interesting is they tell you down here, they aren't the same pieces, obviously, but they are equivalent forms, kind of like 2/4 is equivalent to 1/2, but they look different. So it's talking here about how you can make them look the same. You don't have to do that, but just so you can see how they are connected. And then just here's some more information about how it connects to Cal A with the net change theorem. So you can read this on your own above example 3 on page 864. And then here they're talking about using line integrals. You have curves that you can piece together from different pieces, etc. And then for more general regions here on page 867, we have multiple curves. My daughter comes to say hi. Say hello.
Hello.
You don't want to be in the video?
Not really.
No. Okay. Say goodbye.
Bye.
Hi, puppy. Okay. So page 867. Let's look at some problems. Hopefully you have read all that stuff that I highlighted. Now we're going to look at some examples. Page 867, 1 through 4 was where we're going to start. So here it says verifying Green's theorem. This is long. I'll just go ahead and warn you. This first problem is long, but it's a good thing to do for you to understand kind of how Green's theorem connects to what you did before. So they're having you do it 2 different ways. One is the line integral and one is the Green's theorem form, so that you can appreciate Green's theorem and kind of how much work and effort and trouble and whatnot that it saves you. So it says verify the conclusion of Green's theorem by evaluating both sides of equations 3 and 4. So what they're talking about, this Theorem 5, that's equation 4. See this 4 here? And then Theorem 4, that's equation 3. You would think they would make Theorem 4 be equation 4, but no, that would be too easy. So no, this is what they're talking about. Equation 3, so you're going to use this one and this one. So you're evaluating this line integral and then this double integral. That's for equation 3. And then for equation 4, you're evaluating this one as a line integral and this one as the double integral. So that's the 2 things that they're talking about. So it's really 4 things. You're really doing 4 things, 4 problems for the price of 1. You gotta love that. Okay, so these are again 2-dimensional. The domains for all 4 of these problems: circle centered at the origin, radius A. So it would be, that's the closed curve, and then it's everything inside of there for t between 0 and 2 pi. And all of these, the curve is given by this, which when you have cosine in the x and sine in the y, then that's going counterclockwise. So it's going around this way, counterclockwise, which is what we want to do because counterclockwise is the positive orientation for Green's theorem. So that's good that it's going in that direction. All right, so we're going to do number 4. Oh, I guess it would help if I showed you my notes. Let's time out and take a look at my notes. I forgot to show those to you. I'm so excited to get to Green's theorem. Actually, I'm really not. I'm not a huge fan of chapter 15, but for your sakes, I'm trying to be enthusiastic about all of this ridiculous physics because, you know, I guess it is still kind of math. So, sorry, my cord for my headphones was caught in my rolly chair. Okay, here we go. Divergence, circulation density. This was also flux density. I forgot to write that. But divergence is also flux density. This is circulation density or curl. If you're doing counterclockwise, you've got positive. Counterclockwise is positive. Clockwise is negative. All right, and then this is the one for flux. So C is the closed curve. R is the 2-dimensional region that's enclosed by C. So you've got C on the outside, the region on the inside. Here's the F. What is that noise? Oh, it's raining. Okay. I guess that's what happens when you have skylights. It makes it really loud when it rains in here. Hopefully they won't start leaking. I'm on the opposite side of the room from the leaky skylights, so we should be good. We'll see. I don't know. Okay. All right. Then the other form of Green's theorem. So you've got circulation and curl. So that's all the formulas. So when they ask for flux, they're wanting you to use this one. I highlighted it so you could tell. And when they ask for circulation, they're wanting you to use this one. Okay, now let's get to this example. Okay, so started with all this preliminary stuff. The M is the thing in front of the I, the N is the thing in front of the J. Here's my r of t. So this is my x, this is my y. There's my bounds on the t, so I drew the picture. Circle centered at the origin, radius a, it's going counterclockwise, which is what I want. So now I'm going to find, I'm going to go ahead and find all of my stuff first, and then I'm going to use it in the appropriate pieces. So here, excuse me, here is the functions of t. The m and n is functions of t. Okay, sorry, my brain died for a second. That happens when you get old, so appreciate your brain while you're young. It gets really bad after a while. Okay, so here, this is my m. I plug in for x and y. Again, here's my x, here's my y. And squaring, so this is a squared times another a, that's where the a cubed comes from. Same idea here, squaring is a squared times another a, that's where the a cubed comes from. So this is m and n as functions of t. Now here was my x and y, and I'm going to need the dx dy, so I'm taking the derivative of this to get dx, the derivative of this to get dy. And then I also need all of these partial derivatives, m with respect to x and y. And I paired them up across the way they go. Mx goes with ny, and my goes with nx, so they go together in pairs across. It doesn't really matter what order you put them in as long as you know where to plug them into your formula. But these are, again, this is the m and the n, so these are the partial derivatives. And now I think, yeah, now I have all of my pieces. Okay, so now that I have all my pieces, here's Theorem 4. The left side, it needs the m and the dy and the n and the dx. These are where you need the t's. So the left side, you're using t's. Over here, you need the dn dx, dn dy. So over here is where you're using the x's, right? So for the left side, you have to do both sides. So you're doing the left side and the right side. So for the left side, which is this one, again, that's functions of t. So your bounds on your t were 0 to 2 pi. You're plugging in for the m and the dy and the n and the dx. So that's up here, m, n, dx, dy. Plug all that in. Simplify. And, sorry, it wouldn't all fit. There's part of it. There's the rest of it. I should have put parentheses. Oh, never mind. I have a dt on both pieces. I'm good. Both pieces. Okay, so it's this here. Then I can factor out what they have in common. They each have an a to the fourth and a cosine and a sine. I went ahead and factored out the negative so that this would leave me with cosine squared minus sine squared, so that I can use a trig identity. So I use, oh, just kidding. I was going to use, I remember now, that's why this whiteout is. I was going to use cosine squared minus sine squared is cosine 2t, but then it was going to mess me up having this other cosine, so that didn't work. That's what all that whiteout's about. So this is going to work. This is something different. So cosine is the same, sorry, cosine squared is the same thing as 1 minus sine squared. And then you have another minus sine squared here, so it's this. And then notice you have sines and sines, so you can let u be sine. And then you'll be able to cancel this cosine. The a is just a number, so don't worry about it. It's just a number. It doesn't affect you at all. Let's slide this down. Hold on, I gotta get situated. Okay, there we go. I just recopied that same line from the previous page since I was switching pages. So I can't integrate a product, so I have to distribute that u. So when it's this, after I distribute the u, it becomes, well, after I distribute the u, it's this. Then after I integrate, it's this. And then I put back in what my u was, which was sine. But then, because it's 0 and 2 pi, and these are both sines, sine of 0 and sine of 2 pi are 0, so the whole thing is just 0. Okay, so that's just 0. So my flux here is 0 is what that's telling me. Now I'm going to do the right side. So it's this same equation, but the right side. I just learned a very important lesson. I learned a very valuable lesson just now. Do not eat cookie dough right before you make a video, because then during the whole rest of the video, you just want more cookie dough. That's all you can think about is more cookie dough. So note to self, do not eat cookie dough before making a video, because now I want more cookie dough. Okay. I'm not going to go eat any cookie dough right now, though. I'm going to wait till this video is over. For your sake. You're welcome. Okay, this is the right side. So I already found these on the previous page. Hold on, time out. I'll show them to you. Here we go. They are here and here. And then for my bounds, this is my circle. And so it was x squared plus y squared equals a squared. So if you take x squared plus y squared equals a squared, and you solve it, oh, I showed the work right here, good. X squared plus y squared equals a squared. I solved it for x just because they always write dx dy, so I just always do x first just because that's what they always write, but it really doesn't matter. You could have solved it for y and it would have been perfectly acceptable. But I solved it for x, so I have the plus or minus because it's the whole thing. So the minus is on the bottom, the plus is on the top. And then notice what happens though for my function. I really didn't need that because notice what happens for my function. It's just 0. So if you're integrating 0, it would be 0 if it's a definite integral, c if it's an indefinite integral, but this is a definite integral, so just 0. So notice here I got 0, here I got 0. So that's what I was trying to show. It said verify the conclusion of Green's theorem, which is saying show both sides are the same thing. So there you go, done for the flux. Now let's move on to Theorem 5. This is showing that it's the same thing on the left side and the right side for the circulation. All right, so here's my left side and my right side. I'm still going to use the same pieces that I had from before. So again, these are functions of t. So I'm plugging in, I get this. This is the rest of it. It wouldn't all fit on one line. Add them together. And cosine squared times sine squared. I did the work over here. Cosine squared times sine squared is the same thing as cosine times sine squared. And then I can bring in a 2 if I also bring in a 1/2 to cancel it. And then 2 cosine t sine t is sine 2t. Then I square everything, and it's 1/4 sine squared 2t. So well, not the 2a to the 4th, that's over here. But all of this becomes this. So I can do 1/4 times 2, which is 1/2. And then the sine squared becomes 1/2. 1 minus cosine of 2 times normally t, but now 2t because there's already a 2 there. So it's really 4t. Okay, so the 2 times the 1/4 was the half. This other half came when I changed the sine squared over, and then the 1/2 times the 1/2 gave me the 1/4. So this is what I'm integrating. Again, the a is a constant, so ignore it for integrating purposes. Okay, so here is what I get when I integrate. Plug in my 2 pi and my 0. This is sine of 8 pi, which is also 0. So it simplifies down to this. So now for my right side. For my right side, I have the same bounds, but notice a different function. So here's my bounds, different function. So when I integrate, that would be a huge pain. You can try that, and it would work, but it would be a huge pain. So because this is a circle, it's a whole lot easier if you switch to polar. So again, you don't have to, but it makes your work so much better. So if you switch to polar, because you had a circle centered at the origin radius a, theta is between 0 and 2 pi, r is between 0 and a, y squared plus x squared becomes r squared, dx dy becomes r dr d theta, so it's r cubed. Integrate, super easy this way, super hard the other way, and I get the same thing. So notice this answer and this answer, same thing, and so it's the same on the left and the right for circulation also. So those problems are long. You only have one of them for homework, but it's a good way for you to see the connection between the line integrals that you were doing in the first part of chapter 15 and Green's theorem here. And so it's a different way, just a different way to do it. And a lot of times Green's theorem is a lot easier. Okay, so, sorry, the sun is shining. It's apparently stopped raining now, and the sun is shining through the skylight, so that's why it's so bright. This weather today is crazy. 1 minute it's raining and 1 minute I can't even see because it's so sunny. I'm not going to complain about the sun. I will complain about the rain, but I am not going to complain about the sun. Okay, 5 through 14. Use Green's theorem to find the counterclockwise circulation and outward flux. So circulation and flux, that's Theorem 5 and Theorem 4 for this vector field and this curve. All right, number 8 is the one I'm doing. Okay, hold on 1 second. I gotta write something down. You know, that's why I always have something written on my hand, because I can never remember anything if I don't write it down. So, okay, sorry. So for flux, we're going to use the right side because this is the Green's theorem section, so it makes sense to use the Green's theorem one instead of the line integrals. And just as a side note, hold on, while I'm thinking about it, you didn't really appreciate, well, I don't know, maybe you did appreciate it, but you couldn't truly appreciate how much trouble Green's theorem saves you on number 4, because number 4, it just had a single curve, just the circle. And so you only had to do a single set of parametric equations. But something like this, like say number 5, for instance, number 5, because it's a square is made up of 4, well, they're not really curves, but we're going to call them curves. 4 curves, 4 sides. So you would have had to have 4 separate sets of parametric equations, 4 separate bounds, 4 separate functions, 4 separate of everything. So you would have basically been doing 4 problems for that. But with Green's theorem, you can do just one, because instead of looking at it as the 4 different sides of the square, you can look at it as the one region that's enclosed by the square. So instead of having to do it as separate curves, you're doing it as a single region. So Green's theorem is fantastic. It's a huge time saver. But keep in mind, Green's theorem, you can only use it if your curve is closed. So it has to be closed and form a region inside the curve. So you can't use it all the time. But this one is mine, number 8. It's a triangle, so it's obviously closed. And it's bounded by these 3 lines. So I'm going to first, this is my M, this is my N. But be careful here. This negative has to get applied to this N. So the N is not x squared plus y squared. The N is actually negative x squared minus y squared. So be really careful on the signs. Okay, so here's my M. Here's my N. Take the derivatives, M with respect to x, N with respect to y for the flux. And then for my region, I did my bounds up here. Again, just because they always write dx and then dy, I'm just going to integrate dx, dy. But if you want to do it dy, dx, you'll get the same answer, but your work will look different. So here, for the x's, notice on the x's, on the left is this line, and on the right is this line. So on the left would have to be the y, and on the right would have to be the 1. So make sure you get that set up in the right order. Okay, so this is the easy integral. I'm integrating, and keep down. Okay, plugging in, and so this is what I have for my flux. So my flux is 1/6. Okay, now let's look at it for circulation. Circulation, different formula, similar principle. So again, here's my same N and N, but now I need different derivatives. So I need the derivative of M with respect to y this time and N with respect to x. So same bounds, different function, integrate, plug in, and this is my circulation, negative 7/6. All right, so on those, again, the 2 different forms of Green's theorem are giving you 2 different things. Okay, so next group of problems. Hold on, I gotta read the directions. Oh, the sun is so bright, I can't see. Okay, number 16. I don't know if you can see that. I can't really see that. Maybe that's better. Okay, find the counterclockwise circulation and the outward flux. So notice it's circulation and flux again of the field around and over the square. That sounds funny. The square cut from the first quadrant by the lines x equals pi over 2 and y equals pi over 2. Okay, so because it's the first quadrant, it's also bound by x equals 0 and y equals 0. But here's x equals pi over 2 and here's y equals pi over 2. So this is a easy square with 4 constants for the bounds. So here, because I'm going to have to do both, I just went ahead and did all my derivatives together. Here's my M, here's my N. I did the derivatives going across as they go together. So this is for flux and this is for circulation. So for my bounds, again, super easy. Again, I did x first just because that's what they usually do. Plugging in, then simplifying, and then plugging in, simplifying, etc. Here's my flux. So negative pi squared over 8. And then circulation, same idea. I guess I should have let you try this one on your own. Sorry, I totally should have let you do that. Pretend like I did and pause the video and rewind and then try it yourself. See, magic. It's a wonderful thing about videos. Okay, anyway, here's the circulation. It is pi. All right, let's see if you want to try this one by yourself. Hold on, don't look. No, probably not. These next 2 are kind of weird. So sorry, I got nothing for you to try by yourself this time. What a colossal fail. Oh well, too late now. Okay, number 20. Let me move it so it's not in the sun. Okay, find the work done by this vector field F and moving a particle once counterclockwise around the curve. So number 20, here is my F, so M and N. Here is my C. Here is my circle centered at the origin radius 2. This would be hard. This would be hard to work with because if you were going to do it in terms of x's and y's, you would have to solve this equation for either x or y, which you're welcome to try on your own, but that's not easy. So I'm going to do a little bit of math magic here. It's not really math magic. It's just a creative getting around a problem that you can do on something like this where your circle's crazy. Okay, so I'll show you that in a minute though, so hang tight for some math magic. Work, this is the formula from, I don't remember what section, they're kind of all running together at this point, but one of the sections in chapter 15, 15.2 or 15.3, the formula for work, it was a line integral. And then line integrals you can use Green's theorem for, so this is the Theorem 4, the circulation one that I'm using here. So I have the left side of the line integral, and this one's what I'm actually going to use computationally. So this is what I'm using. So I find, well, I didn't find, here's my m and n they gave me. I found my derivatives, and then when I plug them in, I get 4. Notice I haven't done my bounds yet. Here's the math magic. Ready? Magic. If you factor out the 4, what you have here is the double integral over region R. The function is 1, and then it's dx dy. So if you remember double integrals, when the function is 1, that represents area. And so if this is area, then you can find the area of this. That's something geometrically that you know how to do. It's just a circle. So for area, it's just pi r squared. So it's 4 pi. So this whole thing here is just 4 pi. And then you multiply it by the 4, so it's just 16 pi. So if you want to, if you're feeling up to a math challenge, you can go back and do this not doing it my math magic way. And you can go back up here, solve it for x or y. You could switch to polar, but since it's not centered at the origin, it's difficult to switch to polar too, because switching to polar is pretty tricky. It's not going to be, you know, r is 0 to 2. That totally won't work. Don't try that. You're going to need some sort of trig function involving theta, and I don't have that memorized, so I don't know what it would be. But it's pretty tricky even to switch it to polar. So if you want a challenge, you can try that some other way, or you can use my math magic way. That works when it's a geometric shape that you know and when you're integrating just a 1. So this would only work if this was a constant that I could factor out. If that would have been like an x or a y or something in there, no math magic on this one, sorry. Okay, 22, last one. This is, oh, I guess it would help if I read the directions. Okay, apply Green's theorem to evaluate the integrals. So we're again using that circulation one, the Theorem 5. And this is my M, this is my N. I have the derivatives here. This is the Theorem 5 one that I'm using. They give me this curve. Oh, they already gave it to me. Super easy. They already gave me my curve. This is what it looks like with my region. Notice here, you have to switch them. Well, you don't have to, but if you don't, you're going to have to go back up here and solve this for x. Unless you want to go back up here and solve this for x and have an inverse trig function, which who wants an inverse trig function if they don't have to have one? You need to do dy dx this time. I've been doing dx dy, but you cannot have variables in your outer limits of integration, so you could not have done dx dy on this one because then the y would be 0 to sine x and you'd have a variable on your outer limit of integration, and that is not okay. So unless you want to have inverse trig functions, you're going to have to do it this way. All right, so this is -1. So I integrate, plug in, simplify, integrate, plug in, simplify, and I get -2. All right, so that's Green's theorem. I hope you enjoyed it as much as I did. And if you have any questions, send me an email.